welcome to the final session of Machine Learning for Humanists. Today we're looking at word vectors, which I think many of you may have heard of because they're a very popular technique these days. So as per usual, there's a programming notebook, which you can access here on the GitHub page, or there's the direct link. And I'll begin by, as usual, by explaining the algorithm with some PowerPoint slides, and then we'll have a go at implementing it. And compared to last week, the code for this week is really simple. In the GenSim package for Python implements the algorithm we're looking at, and you can just use that that pattern that we looked at in week 1 of model, define the model, and then fit it on the train it on the data, and then use some methods built into the model to do the inference part, the actual using of the model. So we don't, it's not like last week where there wasn't any readily available code and I had to write a whole bunch of code, which then inevitably had some bugs in it, unfortunately. Though I hope maybe some of you have revisited last week's notebook, and the version that's online now shouldn't have any bugs. So if you've had a look at that, you should be able to get it working. Okay, but this week we're doing word vectors. So I hope everyone can see the slideshow there. Just I'll just make sure the chat window's open and just let me know if you have any issues. So what are word vectors? Basically, they're a way of trying to represent the meaning of words mathematically. Now, I say represent the meaning of words. As we've looked at in previous weeks, there is an issue with talking about meaning when you're talking about computers, because a computer has no idea of reference. It's unable to know that a word refers to something in the world. In fact, there are some AI systems that try to give computers some awareness of the outside world. Like, for example, by combining a system that can see with a system that can read text. And you might then combine that with a system that can actually reach out and touch things. And perhaps by combining those 3 different things, the computer could be said to have some awareness that there's a world to which words refer. But even then, not really. So the way the computer works out the meanings of words is simply to observe the way words co-occur in a text. Which words tend to be used in similar contexts, which words tend to be used in dissimilar contexts. So word vectors in this regard are quite similar to topic models, but there's a crucial difference. In a topic model, you're trying to sort words into buckets, which, the topics. You're trying to find clusters of words that tend to occur together. And the idea behind the model is that when a bit of text is created, the words from the text are selected from a small number of topics. So this text is about fishing. So you would expect there to be words like rod and boat and hat and sun cream and so on. This text is about medicine. So you'd expect words like pharmacology or choledocholithiasis to appear. Because these are words that come from the relevant topic. Word vectors don't do this. Rather than clustering words together, what you try to do is come up with a set of numbers that represents the meaning of each individual word. And the technique can then be used to cluster words, but it isn't itself a clustering, it's not itself a form of cluster analysis. It's actually trying to represent each individual word separately. So on this slide, is an example of how this might work. This is a kind of a great simplification and somewhat of a misrepresentation of how word vectors work, but it gives you the idea. So we could imagine if we had these 7 words here, rose, car, cloud, blood, wine, juice, sea, we could imagine trying to represent the meaning of each of these words just using 2 numbers. So here on the table on the right, you can see we've got each word, and each word has 2 numbers associated with it. And then because it's just got these 2 numbers, we can conveniently plot the words here on a graph on the left. Obviously these are just made up. I've contrived this example completely just to show you some ways word vectors might work. But you can see, for example, that in the top right here, we've got a bunch of things that are liquid, so they tend to be a bit closer together. And in the bottom left, we've got a bunch of things that are solid or more solid. Obviously, clouds are actually liquid if you know the mathematics, but if you know the science, sorry, but people often think of clouds as not liquid. So we've got things that are less liquid down here. And you might also notice that to the top left, we've got things that are more red, like rose and blood and wine. And as we go further down to the bottom right, the things become less red. So this is the aim of word vectors. You want to come up with a set of numbers for each word that captures some aspect of the meaning of the word. So in this case, this model seems to capture the liquidness of the words or the liquidity of the words, and also to capture the redness of the words. Now, there's a few things I just want to point out that, again, I've really contrived this example to make these things obvious. The first is that if you were just thinking about this naively, or not naively, using your common sense, what you might want is for each number of the word to represent a particular quality. Like you might want this column, X1, that could be the column that represents the liquidness. The higher the number, the more liquid the thing is. And you might want column 2 to represent the redness. The higher the number, the more red something is. That would be great if that's the way word vectors worked, because then they'd be interpretable by a human. The numbers, the columns, would actually correspond to human concepts. But that's never how word vectors work. Most word vector models don't just have 2 columns. They have 200 or 300 or 400 columns. You normally see most famous word vector models are in the hundreds in terms of the set of numbers that define each word. And it's just never the case that those 200 columns correspond to 200 things a human would care about. So I've tried to show that in this example, why you can see that these 2 qualities of being liquid and being red, they're not parallel to the axes. You know, as things get more liquid, both X1 and X2 go up. So, you know, wine, for example, has quite high scores for X1 and X2, 6 and 8.5. Whereas car has quite low scores for both of them, 1.5 and 3.9, because as things get more liquid, both X1 and X2 go up. And similarly, as things get more red, X1 goes down and X2 goes up a little bit. So you'll see, for example, that rose here, which is a bit more red than car, is actually lower on X1. So rose is 1.2 on X1, whereas car is 1.5, but it's higher on X2. Rose is 6.9 and car is 3.9. So the technical term for this is the word vectors are not orthogonal. The different these lines here that represent these different concepts, they're not at right angles and they don't map onto the axes. So that's the first thing I wanted to point out to you, that these word vectors, they tend to cluster the words together, or, you know, they tend to represent the words so that words that are related in meaning are close together in the space. But unfortunately, when you train these word vector models, the axes, the actual numbers themselves, don't have a human interpretable meaning. The other point about this is, as I mentioned already, that in this very contrived example, there's just 7 words and they're represented by 2 numbers each. In real world word vector models, you normally have tens or hundreds of thousands or even millions of different words, each of which has a vector representing it. And the vector, the set of numbers representing each word, would normally be much more than 2 in length. Typically, as I said before, 2, 3, 4, 500 numbers would be the usual dimensionality, which means, of course, that you can't display word vectors easily on a graph like this, because there's no way of drawing 300 axes in a way that a human could understand. Our sensory organs simply don't work that way. So, right, so that's the aim. The aim is to come up with a set of numbers for each word in your corpus that somehow captures something about the meaning of the words. So there you go. Sorry, that's just to indicate a vector is just an ordered set of numbers. So in this case, there's the word vector for rose. It's a 2 vector There's two numbers in it, so that's how you represent it. Two real numbers, R2, and the two numbers are 1.2 and 6.9. So that's the vector for the word rows. So when we talk about a word vector, what we're talking about is this set of numbers that corresponds to a particular word in the model. To explain how you can use a neural network to generate these word vectors, I want to go back to an example we've already looked at. So this is a network we looked at last week. It's basically the same as the very first neural network we looked at, the one that could take 4 measurements from a flower, an iris, and predict which of 3 iris species it belonged to. But this is one that's been adapted for language. Let's imagine we wanted this network. So I'm just going to revise what this network does, and then in the next slide I'll show you how you can adapt it to create word vectors. Imagine we wanted to predict the next word in a sentence. We could show the network the word cat, and we would want it then to predict which of the many words in the vocabulary are going to come next. So one way you could do that is this. We represent the cat as a one-hot vector. So if the so-called one-hot vector, so if cat was word 3 in the corpus, in the dictionary, sorry, then this vector would be a big long set of numbers as long as there are words in the corpus. So let's say there were 10,000 words in the dictionary, sorry, you'd have 10,000 numbers, all of which are 0, except for number 3, which would be 1 to represent that this word is cat. Then you have these neurons here, and each of these neurons has a set of W's, of weights, which it uses to multiply the input. And of course, in this particular example, because the input, every single number is 0 except for 1, actually all of these W's drop out of the equation, except for the one W that corresponds to the word. So in this case, only weight number 3 would be used, because all the other weights would be multiplied by 0, and you just end up with weight number 3 times 1 plus perhaps a constant that's also been worked out by the network. And then eventually you might have extra layers that then process the output of these 4 neurons here. Each of these 4 neurons would have its own set of weights and would consider what it thinks of the word cat. Then you might have some later neurons that then interpret the output of those neurons. And eventually you get to the output layer, which would then try and predict what the next word would be. And one way of doing that is to use a softmax function, which outputs a set of numbers like this. There'd be one number for each word in the vocabulary. And the higher the number, the more likely the network thinks it is that that corresponding word will be the next word. So in this example here, this contrived example where there's only 4 words, it thinks that word number 2, whatever that happens to be, is most likely to be the next word. Okay, so that hopefully that has jogged your memory about the idea of a neural network and how it manages to get from an input to an output. How could we use this to come up with a set of word vectors for each word in the corpus? Well, let's just take the first part of the neural network and consider that, and you'll see where these vectors can come from. So here we have the input. Now remember, the input in a language model is going to be a one-hot vector. So there's just going to be one number per word in the dictionary, and in any particular instance, every single one of those is going to be 0 except for one of them, the one that corresponds to the position of that word in the dictionary. Then we have a bunch of neurons that examine those words. Now, we've seen before that you can represent a neuron as a linear equation like this. Okay, so you can say, here's the neuron number 2 in layer 1. It's got a bunch of weights, its own internal weights, 1, 2, 3, 4, as many weights as there are words in the dictionary. And when a word comes in, it multiplies those weights by the incoming vector, which means most of the weights get multiplied by 0 and just one weight gets multiplied by 1, and then it outputs the sum. Okay, so we can actually represent all the neurons at once. So this equation just represents one neuron. You can actually represent all the neurons at once in a matrix. So what's this matrix? This is a set of numbers. And by the way, I'm just ignoring the bias here, the B. So just the B is still there, but I've just left it out just to simplify this. Here's a matrix. Each of these W's is a number. Each row corresponds to one of the neurons. So here we can see, here's neuron number 2, right? So row 2 represents neuron number 2. And in this very contrived example, there's only 4 words in the dictionary. So there's just 4 weight variables. There's number 1, number 2, number 3, and number 4. So each row represents a neuron. There's 4 neurons in this layer, so there are 4 rows. If each row represents a neuron, what does each column represent? It says a word. That's exactly right. Yes, each column corresponds to a word. So how is that? So imagine we get the word cat and it was word 4. Okay, so this is what the, I've changed it. It was word 3 on the previous slide, wasn't it? But it doesn't matter. Imagine if cat was word 4, its vector would look something like this. Actually, technically, it should be a column vector. I've got it as a row vector from side to side. It should actually be a column vector up and down, but it doesn't matter. I've put it up here so you can clearly see. When you multiply this vector for cat by all of the neurons, as we know, weight 1 times 0 is going to be 0. So that's going to drop out of the equation. That's going to drop out. That's going to drop out. That's going to drop out. These are all going to be multiplied by 0. So they're all going to drop out. These are all going to be multiplied by 0. So they're all going to drop out. These weights here, the 4th weight variable in each neuron, they're going to be kept. This set of numbers here corresponds to the word cat. So the basic idea for calculating word vectors is this. You set up a neural network like the one on the previous slide, and you get it to run on a whole bunch of training data. And then at the end, you discard most of the neural network. The part of the neural network that takes the information and predicts what the next word is or whatever, you get rid of that. And what you just keep is, from the hidden layer within the network, you just keep this matrix. And each column is going to correspond to one word in the dictionary. And this column is going to be the word, and each column is going to be the word vector for that word. So the word vector, the numbers, they're actually the weights from a neuron that's learnt to do something with those words. So the question is this: what network should you use to get these weights? You actually don't use the network I showed you on the previous slide. I just showed you that one because it has the same structure as the original neural network we looked at. It's the very simple structure of a so-called feed-forward neural network. A guy at Google in 2013, Thomas Mikolov, put forward a different algorithm in 2 papers called word2vec. It's actually not just one algorithm. It's a whole bunch of different algorithms that all do the similar thing. So I'm actually going to show you one of the algorithms he came up with, which is called a skipgram model with negative sampling. He also, later on, after moving from Google to Facebook, developed another quite cool word vector algorithm called fast text, which you might like to look up, which actually splits each word into its component parts and then calculates a word vector for each of those parts. And then each word is represented by the average vector of all the parts that it's made up of. And that one's actually very powerful. And it can, because it knows it has a vector for each part of which words are made up of, it can actually produce a vector for a word it's never seen before by splitting that word into its parts and then summing the different vectors that it already knows together. So that's quite cool. This guy, Thomas Mikolov, is the guru of word vectors. Anyway, I'm going to show you this word2vec skipgram model with negative sampling. So the first part I'm going to explain is the skipgram part. Here's a diagram of how a skipgram model works. The idea is this. This is the problem you're getting the network to solve. Given a certain word, cat, for example, you get the network to try and predict what words appear nearby. So in this example on the screen here, we will have set a window size of 2, which means it looks 2 words either side of the word cat. And the task for the network is to predict what other words appear in that 2-word window either side. So, you know, in a real example, the sentence might be, a black cat walked by. So you would hope that the computer, the network, would spit out higher numbers for up, black, walked, and by than for other numbers in the corpus, for other numbers in the dictionary when the word cat appears. Now, it's called a skipgram model for this reason. A gram, for whatever reason, I actually don't know why this is, refers to a certain number of words, a phrase of a certain length. So a bigram is 2 words, a trigram is 3 words, an n-gram is n words, an indeterminate number of words. Could be 10, could be 100, could be 1, an n-gram. It's called a skip-gram because, well, the middle word is skipped, So there's a black, skip, walked by. It's a skip-gram model. You take out the middle word and try and predict what the other words are in the n-gram. So that's why it's a skip-gram model. So this is the network you train. So yeah, given this word, predict which words appear nearby. And in this particular example, we have a window size of 2. Now, I've used the word W here to mean word. I realize it's a bit inconsistent because on previous slides, it's meant weight within a neuron, but it's just word. And T minus 2 means, in natural language processing, we normally think of words unfolding in time. So each word is a new time interval as the sentence unfolds. So T minus 2 means 2 words prior. T minus 1 means 1 word prior. T plus 1 means 1 word after. T plus 2 means 1 word after. So essentially, it's a pretty straightforward sort of neural network. You train the model so that it learns to predict what other words are likely to appear nearby for each word. And then at the end, you discard all this part. And you just extract the weights from the neurons, and that gives you your word vectors. Now, you don't actually have to discard this part. You can keep this part if you want to train the network further. But once you've finished training it, normally then you've got a decent set of word vectors that works, and you just discard this bit. That's what normally happens. And then people publish the set of word vectors and they use them for various things. Okay. Right, so the next part is this bit negative sampling. I said that he proposes a skip-gram model with negative sampling. What's the negative sampling mean? The negative sampling simplifies the calculation in a way that I may not really be able to explain to you very well, but it also accelerates the training. This is how you do it. So on this previous slide, I suggested that each time it sees one word, it predicts 4 words. In negative sampling, you do something a little bit different. Instead of just giving it one word and getting it to spit out 4 predictions of what it thinks the most likely words are, you instead create a set of words where you have some true examples and some false examples. So in this example here, you'd create 4 training examples: cat and cat and black, cat and walked, and cat and by. And then you would randomly generate a whole heap of false examples, like cat and budgie, cat and Marmite, cat and iPhone. And the positive examples, okay, what you want, you then, for the positive examples, you give the value 1, and the negative examples, you give the value 0. In most examples of this, you generate something between 5 and 20 false examples for every positive example. And I hope you can see why you do this. It's then the network learns, okay, cat is related to these words and it's not related to these other words. So you've got sort of pull factors and push factors. The word cat is getting pulled towards certain words and pushed away from certain words. So it speeds up the training of the network. It also simplifies the calculation for this reason, that you slightly alter the output layer. So in this version here, each of these 4 outputs, okay, is going to spit out, say, 10,000 numbers. If there were 10,000 words in the vocabulary, each of these is going to calculate 10,000 numbers. And we would hope that for this one here at the top, the word A has a high number among the 10,000. In this one, we'd hope the word black has a high number among the 10,000. In this one, we'd hope the word walked had a high number among the 10,000. So there's a lot of calculations going on every time. It's got to spit out 10,000 numbers and predict for every single word in the vocabulary each time. In this one, you simplify it. Let's say, again, the vocabulary had 10,000 words in it. What you have at the end here is 10,000 little predictors. Okay, this one here predicts whether, given the input, the output is going to be budgie. Okay, and it gives a value between 0 and 1 because it uses a sigmoid function to to squash its output into about a range of 0 to 1. And we ask the network to output 0 if it thinks budgie shouldn't appear, and 1 if it thinks budgie should appear. This one is the predictor for black, and it's going to spit out a 1 if black is in the context, is within the window, and it's going to spit out a 0 if black isn't within the window. And likewise for all the other words. So you've got 10,000 of these. And so for each training example, okay, it only uses one of these predictors. So if the training example is the input word cat and the output word budgie, and this is a false example, so the value should be 0, well, it just ignores all these other neurons for that calculation and just uses this one. And given the input cat, it should output 0. And then let's say the next example it looks at is the pair cat and black. Well, when it looks at this example, because it knows the output word is black, it's just going to ignore all these other predictors here. And it's just going to examine the word cat using its inner neurons and then make a prediction whether the word black is in the context. And in this training example, black is in the context. So the network will, punish and correct itself if it doesn't output a value near 1. During the training, it'll look here, and if the value that gets spat out by this predictor is 0.3, it'll go, oops, that's wrong, and it'll adjust the weights of all the word vectors so that next time, this black predictor is more likely to output a number close to 1. And so on and so on. So this negative sampling, there's two things here. The one is that you're providing lots of negative examples, okay? Cat, the Marmite predictor should not output a high number for cat because the word Marmite rarely appears in the context of cat. But the word black, it should output a high number because the word black very often appears in the context of cat. So that's the negative sampling part. So it's and this is done. The computer does this automatically. Okay, what it does is every time it looks at a sentence, it extracts the words that are actually in the context. So let's say you had a window size of 2. For the input word, there'll be 4 words that are actually in the context. And then for each of those 4 words, it'll also generate between 5 and 20 negative examples, which it does by just randomly picking other words from the dictionary and then assigning a value of 0 to them. So to the 4 words that are actually in the context, it'll assign a value of 1, creating 4 positive training examples. And then it'll create 20 to 80, depending on what you've picked, negative training examples by just randomly selecting other words and assigning them a value of 0. And then during the training, each training example is actually just an input word, a target word, and whether that target word should have a 1 or 0 associated with it. And the network trains by trying to output the 0 or the 1 appropriately, given the input word and the target and the potential context word. And this skip-gram model with negative sampling has proven to be a very, very effective way of learning very good word vectors. And I'll show you at the end of the presentation how we know word vectors are good. It's actually quite remarkable what you can do with them. So given this input word, does the target word appear? There we go. So this is just a final slide to give you another representation of what we were talking about. So during the training, okay, we had these 4 neurons, cat's word number 4. So what happens is, this again, the network can actually take a shortcut when you're doing this sort of word embeddings. It doesn't, in a normal neural network, every one of the input numbers would be multiplied by all the corresponding weights and then summed together. So when we were looking at the iris example, for example, we had the petal length, the petal width, the sepal length, and the sepal width, and each of those 4 numbers would be multiplied by the corresponding weights in every neuron. Now, actually, in these word embedding models, the computer knows that every single number is going to be 0 except for 1. So what it does is it just chucks out these weights and doesn't even bother doing the multiplication. So actually, these models can be trained quite efficiently because instead of doing, thousands and thousands of multiplications to multiply 10,000 numbers corresponding to each word in the vocabulary by the hundreds of weights from the hundreds of different neurons. It just discards all of the weights and all the neurons except for the relevant one. And then it just gets these 4 weights. It doesn't even bother multiplying them because they're just going to be multiplied by 1 anyway. And it just hands those weights over. It hands those weights over to the predictor. So for example, the word black. And then this predictor is a neuron that has weights associated with each of these numbers in the word vector. It looks at each of those. It multiplies these 4 numbers from the word vector by its internal weights, sums them together, sticks it through a sigmoid function, and outputs a number close to 1 if it thinks black is in the context of this word cat, and a number close to 0 if it thinks black isn't in the context. And as I say, if you have 10,000 words in the vocabulary, you'll have 10,000 of these separate little predictors. And the computer will select the correct predictor based on what you've told it the training example is. If you say to the computer, okay, the training example here is the input word cat and the output word black, and the true answer is 1, then the computer will know to select the 4th word vector, multiply it by the weights of the second predictor, because black is the second word in the corpus, and then output a number, and it'll check to see if it manages to output the correct number based on the training example you've given it. No, I don't think so. What it's like is you could do the multiplication. It's actually like multiplying this weight matrix. Perhaps people don't know about matrix multiplication, but if you imagine this as a column, so it's 0, I can't draw very well, 0, 0, 0, 1. So if you imagine that as a column vector, okay, and you times it by this whole matrix, which we'll call W, okay, the effect of this multiplication, you could do it as a multiplication, but the effect of multiplying a vector like this by a whole matrix is actually just to select column 4. It's not like multiplying by a diagonal matrix. This here is equivalent to just selecting column 4. Yes, it can. Yes, it can. And actually, there's if you look in the GenSim documentation, which is for the package we're using, you'll see it's got a built-in thing called phrases. I can't quite remember how it works, but generally, one of the things you can do with vectors is you can add them together or take the mean of them. So you could create a combined vector for a phrase like New York or whatever. The other thing you can do is you can actually split your corpus up into bigrams. So it wouldn't be hard to have the input word as New York and then predict what else might be in the context. Yes, that's been done. There's been a lot of work done on applying word vectors to phrases. It's quite a well understood problem. You can work with phrases. I can't quite remember the maths off the top of my head. I'd have to do research for you, but you can definitely work with phrases. And the way it's normally done is you add in to your research the use of collocation statistics. So the reason a computer might know that New York is a collocation, is a common phrase, is because the word York is so much more likely to appear after the word new than after any other word. And there's various ways of detecting collocations that have been developed by computational linguists over the decades, such as taking the log likelihood and other sorts of things. But yes, it's been worked on. And if you read Merkolov's original papers, which are linked in the programming notebook, you'll see that he discusses how to apply word vectors to phrases. So maybe I'm flogging a dead horse here, but here's just an example of how negative sampling would work. So you come across this sentence. If the window size was 3, then the context words are out, up, black, crossed, the, and road. And for each one of those, for instance, out, you get the input word and the target word, cat and out, and you give it a value 1, and then you just randomly get 4 other words from the dictionary. Okay, I think I've explained that several times now. So hopefully that skip-gram model and negative sampling makes sense. How do you sample from the negative examples? Well, you just have the whole dictionary and you ask the computer to randomly select K number of words, 4 words, 5 words, 10 words, whatever you want. So you have the dictionary as part of the model. You've already come up with the dictionary. If there's 100,000 words in the dictionary, then you just ask the computer to randomly pick 5, 10, 20 of those 100,000 words. And there's various little bits of tuning. If they're negative examples, the value is always 0. I guess you could implement it so that you guarantee the computer won't pick out. It doesn't really matter. These other words, they're randomly selected. They're so unlikely to be in the context of cat when there are so many. You could rule out from the sampling the words that are actually in the context of the word right now. But words are, there's so many words and their distribution is so random that it doesn't really matter if you sometimes get words that actually do appear in the context of this particular word somewhere else. Doesn't really matter. You just completely randomly select. And some people tune it so that you don't select the words of and the and at and so on too often. But it doesn't really matter otherwise. You just completely randomly select them in general. Okay. Right, so for the final bit of the lecture part, I just want to show you some applications of word vectors and what they can do. And then we'll open the programming notebook and we'll have a go at training our own word vector model. So one of the most famous results of word vectors is that they're really good at learning analogies. So here's a table, a graph from the second paper by this guy Mikolov. And what he's done, his model, which you can download freely, it's there. It was trained on Google News, which had 1.6 billion words in it or something. And it was a 300-dimensional model. So each word is represented by a set of 300 numbers. In this graph, he's used a technique that we looked at in week 1 called principal component analysis, PCA, to kind of squash the 300 axes onto 2 axes so that he can visualize the model. But I hope you can see what's happened here. In these, when you plot the word vectors, here are some countries, and here are their capital cities. And what's quite remarkable, I hope you can see, is that basically each capital city, when you plot it in the vector space, is roughly the same angle and the same distance from its country as other capital cities are from their countries. So in other words, each of these dotted arrows is kind of similar. You know, it's going roughly the same direction and it's roughly the same length. And I said that this is normally seen in the computer science literature as learning analogies. Why is that? Because the question is, Moscow is to Russia as what is to China? Well, obviously, what is Beijing? Moscow is to Russia as Beijing is to China. And you can see that the computer's able to learn that through these vectors here. And actually, you can represent these analogies mathematically. So the origin point of this graph is here. Okay. So if we look, for example, at just the one I just said, here's the vector for Russia. This is how you draw a vector as an arrow from the origin to the point. And here's the vector for China. Here's the vector for Moscow. And here's the vector for Beijing. So how do you get from China to Beijing? Minus the vectors. China minus Beijing will give you this. And Russia minus Moscow will give you this. And because these vectors are roughly the same, you can say that, and am I able to type in here? I don't think I can. You can say that essentially China minus Beijing equals, well, what do you think's on the other side of the equation? China minus, so this vector is China minus Beijing. I'm saying, actually, let me just slightly change that. Let me just say, so it's a bit more accurate. Let's say roughly equals. Roughly equals. So I said this dotted line here is China minus Beijing. So what would, if I say that's China minus Beijing, what can I say about Russia and Moscow here in the equation? China minus Beijing roughly equals Russia minus Moscow, exactly. Now, that might seem a bit crazy, but it actually works. And I'll show you that in the programming notebook. It's actually amazing. It actually works. You can actually do this. What's happening when we calculate word vectors? Two things. Number one is this, that when you do a one hot vector for a word, like let's say cat is the fourth word in your vocabulary of 1 million words, okay, that's a very long vector. It's 1 million words, it's 1 million numbers long. And actually it doesn't contain very much information because only one of those numbers is 1 and every single other number is 0. So one thing we do when we do word vectors is we reduce the dimensionality. So we go from 1 million numbers in that example to 300 by creating a 300 dimensional vector for that word. So it reduces the dimensionality, which actually can really pay dividends in natural language processing systems, that dimensionality reduction. It can make the model significantly faster and more expressive. The second thing, of course, is that you're calculating a lot of information about the word. Just knowing that cat is the fourth word in the dictionary doesn't tell you anything. But by learning word vectors, cat becomes a set of 300 numbers that actually represent, to an extent, its relationship with other words in the corpus. You know, for example, you would expect the word cat to be close to the word dog because they often appear in similar contexts linguistically. And you would expect it to be far away from the word, you know, I don't know, chrysanthemum or something, because it's an animal and chrysanthemum's a flower and chrysanthemum's not a pet, etc., etc. Okay, one final thing I'll just say here with this equation is you can, of course, rearrange it. So if you wanted to ask the computer, tell me what the capital city of Russia is. So no, let's do it the other way. So let's say I want to know what country Beijing is the capital of. Okay, so I'll replace China with X, okay, because I don't know what country it is. Right, so we have X minus Beijing equals Russia minus Moscow. Everyone appreciates that. So X represents China. So we don't know that already, but X minus Beijing equals Russia minus Moscow. And then we could just slightly rearrange the equation by putting Beijing on the other side. So we'll add Beijing to both sides, which means we end up with plus Beijing over here. Okay, so this is this equation you get. If you take the vector for Russia and minus Moscow from it and add Beijing, you'll get a set of numbers out at the end, X. And when you look at that set of numbers, it'll be very similar to whatever the set of numbers is for China. It'll be very similar to the China word vector. If you take the vector for Russia, minus the vector for Moscow and add the vector for Beijing. So remember, each of these is 300 numbers. And when you minus a vector, you literally just, like if you add this vector 1, 2, and you minus the vector 0, 1, the output will be 1, 1. Okay, you just minus the corresponding numbers. 1 minus 0 is 1, 2 minus 1 is 1. So you end up with 1, 1. So if you get the 300 numbers for Russia, you minus the 300 numbers for Moscow and add the 300 numbers for Beijing. The new 300 numbers you get will be the vector for China, or very close to it, which is kind of insane. But you'll see in the notebook that you can actually do this. Okay, so that's the end of the slideshow. What I want to do now is just show you one or two places that word vectors have been applied in the humanities. Then we'll take a short break and then we'll have a look at the notebook. Actually, no, we won't do that. We'll get the thing training and then we'll take a short break while it's training. So I've given you links here to McCullough's seminal papers. Everyone can see the programming notebook now on their screen, can't they? Yeah. Right, so there's some McCullough's papers which you can get. Here are some examples of applications of word vectors in the humanities, just 3 here. This is probably the biggest one. This is the Women Writers Vector Toolkit. It's based on the Brown Women's Writers Corpus. Oh no, it's not. Text from the Women Writers Online, Victorian Women Writers Project, and Early English Books Online Text Creation Partnership. So basically, they got a whole bunch of early modern and modern literary texts, and they trained a big word vector model on it, so that you can explore the words in the corpus. So I don't know what a keyword is. We could look at virtue would be one. So, for example, what this search box does is it finds the vector for the word virtue, and then it uses a similarity measurement. I don't know which one, probably cosine similarity, to find the most similar other vectors in the corpus. So in this corpus of women's writing from mostly the early modern and modern periods, we find that the words that have vectors with the most similar numbers, the shortest distance from their vector for virtue, are innocence, piety, virtue with an E, prudence, genuine, modesty, excellence, charity, virtues. Okay, this is a pretty early modern corpus. This is not the way we tend to speak today, I don't think, when we talk about someone being virtuous. Oh, they're so modest. They have such innocence. And you can try any other word you like. Man. There you go. It's obviously got a lot of religious text in here because man is a creature and a beast and a fool and a beggar. And it's got some other tools here that I can't quite remember what they do. Okay, so, I said before that word vectors are not actually a clustering algorithm, because instead of clustering the words, it just comes up with a set of numbers for each individual word, as opposed to, for example, when we looked at topic modeling. But what you can do, of course, is once the words are arranged in that vector space, you can then use various kinds of cluster analysis. Like an obvious one you could apply is k-means clustering. That would be a really easy one. Get all the words vectors, apply k-means clustering, and then you could see that would clump the words together based on their representation as word vectors. I don't know what clustering algorithm they've used, because they don't say here. They say closest to the center of the cluster. That suggests to me they have used k-means clustering, actually. But here are some clusters that they show. So look, this cluster 10 seems to be full of words that describe the countryside. Plain, hills, water, stream, grove, wave, mountain, maybe also a few words describing the sea. Here's a bunch of words that denote people, Mr., Mrs., William, Edward, George, doctor, etc. Here's a bunch of words about sin and justice and guilt. Now, there might be different ways you want to use this data, but one thing I think it should do is show you that these word vectors actually do learn something very interesting about the words. And here we go. We were just looking at how you can add and subtract words together to do things. don't know how you change the, oh, select not potato. Oh, there we go. So look, we can do an analogy. So here's a famous one. This is the original example. I've done that wrong, haven't I? Okay, man minus king plus queen. Look at what the result is. Woman. There's also some famous examples of how gender assumptions are built into our language, like man minus computer programmer plus nurse equals woman, things like that. People have found lots of these sorts of analogies, and there's actually been research on trying to use mathematical techniques to remove the gender bias and race bias and so on from word vector models. I mean, obviously, so you get some funny things. So man minus king plus queen. Okay, you get man, that sort of makes sense. You get maid, that makes sense. You get salamander. I have no idea what that is, but you can see actually that the closeness of the salamander vector to the output of this equation is much lower than woman. You know, woman, the vector for woman. So let me start this again. If you get the vector for man minus the vector for king and plus the vector for queen, you get a certain set of numbers. Then you can look at that set of numbers you've generated and see which actual word vectors it's closest to. So the generated set from this equation is very close to the vector for woman and also quite close to the vector for man. It's not as close to the vector for salamander. So it's not ridiculous, actually. It's just a bit random. Advanced. Oh, you can do your own equations. And yeah, you can do, they suggest you do this. Orange minus red. So, oh, well, I guess, yeah, so when you minus a color word from orange, it gives you lots of fruits. It sort of gets rid of the color implication of the word orange. That's quite interesting, actually. There you go. That's why they suggest it, I suppose. Words that exist in multiple senses. I guess that's exactly what this example here is showing. That because it's multidimensional, because the word orange is represented by 300 numbers, some of those numbers can capture aspects of the fact of orange as a color. Some other numbers can capture aspects of it as a fruit. Other aspects of it might, other parts of it might capture its political ramifications. You know, this is the advantage of having a 300-dimensional model that actually, you know, in certain dimensions, the word orange could be close to the word red. And in other dimensions, in other of the 300 numbers, the word orange could actually be quite distant from the word red because there's 300 dimensions in which these words are described. So this is one point, though, where word vectors might not be as good as topic models. You know, topic models actually deal very well with the fact that one word could appear in one sense in one context and in another sense in a different context, because the one word can be sorted into different topics. Whereas, yeah, word vectors do project all the words onto a single vector space. So it doesn't cut them up into different topics in that way. So sometimes you might find topic modeling is the better dimensionality reduction algorithm than word vectors. Depends on what you're trying to do. Okay, just to give you two other quick examples. In this paper here, diachronic word embeddings reveal statistical laws of semantic change. They do something quite interesting. They trained a series of word vector models on different corpora. So they got a bunch of texts from, you can see from the 1850s, from the 1900s, from the 1950s, and from the 1990s. And then they saw how particular words changed their position in the vector space in the different models. So here's a great example that the word gay in the 1900s corpus was near these other words, daft, flaunting, sweet. In the 1950s, it seems to have somewhat changed its connotations. It's frolicsome, witty, bright. And of course, in the 1990s, in the 1990s vector model, it's now close to these other words, which you can obviously see. Bisexual, homosexual, lesbian. You can clearly see the shifting sense of the word gay. And similarly, the word broadcast in the 1850s, the vector for the word broadcast is close to the words sow, seed, etc. And obviously in the 1990s corpus, it's near radio and BBC. So I think this is quite a neat application of word vectors. So in this case, you train multiple word vector models on corpora, which contain text from different time periods. And of course, doing it over time is one way, but there's no reason you couldn't have corpora of different kinds. You know, you could have a corpora of American English and a corpora of a corpus of American English and a corpus of British English. You could have a corpus of literature, of poems and novels and so on, and a corpus of technical writing. You could have multiple corpora in many different ways. Time is not the only variable that alters the meaning of words. You could also consider the way other variables alter the senses of words. There's no reason you couldn't do that. But in this paper, they use time as the independent variable. Finally, this is the website of quite a prominent digital humanist from Stanford, Ryan Huser. And in this quite nicely formatted blog post, he shows some results from his experiments using word vectors on 18th century collections online. And what he does is he represents the word vectors as a network like this. This is actually quite a good way of representing high dimensional data, which you can't project onto axes. What he does here is each word is linked to each other word by its similarity. So you use some sort of similarity metric to measure how similar the vector for sensibility is to the vector for vivacity. And then if the words pass some threshold, like the similarity is above 0.7, for example, then you can draw a line between them in the graph. And in fact, you can make the line thicker or thinner, depending on the similarity. So clearly, sensibility, the line here between sensibility and sprightliness is thinner. So the similarity of these vectors must be less than the similarity between the word sensibility and discernment, where the line is a bit thicker. So, and he has, you know, he makes a whole bunch of different comments here about how you can analyze this. And yes, I mean, eventually his book, I suppose, on abstraction in the 18th century will appear, and then we'll see all this more fully explained. So, okay, what I want to do before the break is set this thing to train, because it will take 10 minutes, so we can take a 10-minute break. So the GenSim package in Python, which is pre-installed in Google Colab, but which you would need to install yourself on your machine if you wanted to use it, contains a whole bunch of different code for doing topic modeling. For doing various kinds of language modeling. We used it in week 2 to do topic modeling. It also can do word2vec. It can also do fast text, actually, and also GLOVE, another word vector algorithm. So let's see how you do it. Just execute this cell. What this cell does is from the GenSim package, it imports the word2vec class, which we're going to use to make our word2vec model. And also, GenSim has some really useful tools for learning how to do programming. It has this thing called the downloader, which I've given the nickname API, so it's easier to use. And using this downloader, you can actually download some different corpora. So this time I've loaded the corpus called text8, which is 30 megabytes. So if you execute that cell, it'll import these 2 bits from the GenSim package and then load the corpus. And then down here, so this is the pattern we looked at in weeks 1 and 2 of how to do machine learning in Python. First, we define the model. So it's going to be a word2vec model using certain hyperparameters. Then we fit the model to the corpus, which in this case has 2 steps. So I'll explain that in just a sec. So first thing we want to do here is define some of the relevant hyperparameters. There are others you can define, but these are the really crucial ones. One is the vector size. So we're going to calculate 100 dimensional word vectors. Each word is going to be represented by a set of 100 numbers. Next is the window size. So this is how far either side of the word to look when you're constructing the skipgram model. So we're going to look 5 words either side of each word. Hopefully that makes sense. These 2 variables here, they're specific to this word2vec implementation in GenSim. I showed you a skipgram model using negative sampling. In McCullough's papers, he also describes another kind of model called the continuous bag of words model, which works backwards. So the skipgram model says, given this word cat, please predict what the words are in the context. The continuous bag of words model does the opposite. Given these 4, 5, 10 context words, predict what the missing word is. So if you swap this use skipgram to 0, then it'll use a continuous bag of words model instead of the skipgram model. So let's have it as 1. The other thing is I showed you the negative sampling training algorithm. Another option is to use a so-called hierarchical softmax, which means that instead of splitting the training problem into a series of binary classification problems, you know, the input word is cat, the output word is iPhone, okay computer, please spit out a 1 or a 0, depending on whether you think iPhone is in the context of cat. And in this case, it should spit out a 0 because that's the negative sample. The input word is cat, the output word is black, please spit out a 1 or a 0. That's negative sampling. You could use softmax, which says, please computer, given the input word cat, tell me which of the 10,000 words is going to appear here. Output 10,000 numbers and the highest word should be close to the real, the highest number should correspond to the real word that's in the context. That's the softmax algorithm. You can use that instead, but negative sampling is better. It's more computationally efficient in particular. Theoretically, softmax should create better word vectors, but negative sampling is just so much more efficient that it works better in practice. So we're going to use softmax to 0. And then because we're using negative sampling, we need to tell it how many negative samples to do. With this relatively small training set, we probably should be using more than 5, but we want this training to actually be able to take place in a reasonable time. So for each positive example, we're going to randomly generate 5 negative ones. So we'll set that to 5. So if you execute that cell, you'll see it'll use these 5 variables to configure the model. So now we have something called model, which has those settings. Okay, now to train it, there's 2 steps. The first one is build vocab, sorry. That's where it looks at the corpus and it builds the vocabulary. It looks at what words are there. The guy who made GenSim didn't create the text state corpus. It's a freely available one online. There isn't really a minimum size. You know, generally you want a larger corpus for it to work, but you can just try it. Just try it on your corpus and see if it works. We'll see there's ways of sort of validating it and see if the vectors that it's learned are any good. You can do it with a relatively small corpus. The smaller the corpus, the higher the number of negative samples you should pick. So if you've only got like, say, let's say 200 novels or something, that's actually quite a reasonable amount of text, but let's say you only had a smallish corpus like that, you might pick 20 negative samples. If you've got a larger corpus, then you pick fewer negative samples, like 5. Anyway, you'll see this actually works reasonably well on this text state corpus with these settings. Okay, so build vocab looks at the words. It says how many different words are in this corpus. It builds the dictionary, etc. And then once you've done that, you can train the model. So using the model.train method, the sentences are in the corpus. 5 epochs should take about 10 to 12 minutes. So we'll have our break. And for some reason, it doesn't automatically calculate this. You need to tell it how many examples are in the corpus. So there's this line of code you need to do. If you don't put that in, it'll give you an error and tell you to put this in. So you don't really need me to tell you this. But so we're going to use the sentences. It's going to train on a corpus that we downloaded. And we're going to do 5 training epochs. So it's going to go through the corpus 5 times. So if you just click that and set it off, it should get going. It should take about 10, 12 minutes. So we'll have our break. And then afterwards, I'll show you how to use the word vector model and test to see if it's any good. Righty, everyone, mine's finished. So hopefully most of you are finding that yours are also finishing off. Going back to my contrived example at the start, word vectors themselves are not really interpretable. You can't look at the 300 numbers for each word or the 100 numbers and say, oh, the 100th number refers to whether this is abstract or concrete. And the 7th number says whether it's an animal or not. And the 10th number says whether it's got a positive emotional connotation or a negative one. You normally can't interpret them at all like that. But as I kind of suggest in the example, sometimes you can see that that certain sets of the numbers are correlated and maybe do correspond to something like a human concept. One way of finding that out about a word vector model is to apply cluster analysis or some other dimensionality reduction technique to the word vectors. So, for example, we saw that Mikolov himself uses principal component analysis to display how countries and capital cities are related in the vector space. So he's actually able to show on a graph, which he didn't contrive, some relationship between the different numbers in the word vectors. And what he doesn't show in the graph is how those principal components, those munged together axes were created. But you can actually, when you do the principal component analysis, you can look at the numbers and you can see, oh, this principal component, the one along the bottom that makes the countries to the left and the cities to the right, that principal component is made up mostly of vectors 7, 12, 250, 700, and negatively, it excludes negatively vectors 71 and 306. You can kind of analyze them. And of course, if you do a cluster analysis, like if you look at k-means clustering, for example, you might remember that when you do k-means clustering, for each cluster, you can see the center of the cluster. And the center is just, the center for each cluster will be a set of 300 numbers, because the center for each cluster is also placed into the 300 dimensional space or 200 dimensional space or whatever. And you could look at the cluster and you could see which dimensions it's big in and which it's small in. And when you look at the words that are in that cluster, like if you see that they're all animals, for example, you could see, oh, okay, so animals tend to have higher numbers in columns, whatever, 12, 13, 101, 69. So I hope that answers your question. You can, to some extent, interpret word vectors, but you need to do some mathematical manipulation to them. If you just try and look at them with your naked eye, it's going to be almost impossible. But if you apply some cluster analysis or other dimensionality reduction technique to them, such as k-means clustering or principal component analysis, you might be able to find human interpretable patterns in the word vectors, definitely. Right, now you remember in the talk, I said that when you're doing word vectors, you set up this whole neural network which is designed to do something. So in this case, what our model is at the moment, it's actually a neural network that predicts whether a particular word will appear in the context of some input word. So given some input word, it will predict whether some other word is likely to be in the context or not. So if it thinks the word's likely to be in the context, it'll output a number near to 1. And if it thinks the word's unlikely to be in the context, it'll output a number near to 0. Okay, but we're not actually interested in that at all. You might be, you could be. Maybe in some applications you are interested in that prediction problem, in which case the whole model matters to you. But if your aim is just to get the word vectors, as we've seen, what you want to do is you want to get the hidden neurons and just extract the weights from the hidden neurons. And that gives you a vector for each word in the corpus. And you can discard all of the weights that the model uses to interpret the neuron and to interpret the word vector and predict whether another word's in the context. So this is how you would do that in GenSim. The model has an attribute called WV, which stands obviously enough for word vectors. And that's just the part of the model that we're going to pull out to have as the word vectors. So you can actually pull that out of the model. You don't have to. You could also just leave the model as is. And when you want to access the word vectors, just put this .wv at the end. But if you're trying to build a system that runs efficiently, you might just want to keep the word vectors and forget all the other stuff. So you'd extract the word vectors, by doing something like this, and then you can delete the model afterwards. So by all means do that, bang. Now the model's deleted. So if you want to train it again, you'll have to reinstantiate it and train it again on the corpus, and you'll get different results. But anyway, now we've got the word vectors. There they are. And they're in this particular format, which is unique to GenSim, called a keyed vectors object, which could be inconvenient if you want to plug it into another program, because you'll have to work out what the structure of this keyed vectors object is. But it's quite convenient if you just want to play with the word vectors here in Python, because the keyed vectors object comes with a bunch of useful methods. So for example, you can just pull up the word vector for a particular word by getting your word vectors object and sticking the word in square brackets. So you just try some other words, you know, if whatever you want. There you go, salamander, Chris. I looked up the text state corpus. I can't work out how big it is, but it seems to have been extracted from Wikipedia, by the way. So, you know, just try whatever word you want, and you'll see the word vector. So it's just, we picked a 100-dimensional model. So each word vector has 100 numbers. And you'll see that most of the numbers tend to be pretty small. I believe they're all between -1 and 1. They seem to have been put through a tanh activation function, which outputs a number between -1 and 1. But they all seem to be between -1 and 1, which is not surprising. Okay, so there's the word vectors. Now, if you want to find words that are close to a particular word in the vector space, you can use this most similar method. So here are the words that are closest to the words that have vectors most similar to the word toothbrush among the word vectors. Normal, whatever the hell that is, whitening, centered, drooling, sutures. It seems to have learned something. Maybe some of these other words are a bit like, I don't know why skated is near toothbrush, but it seems even just after 5 epochs with only a 100-dimensional model on this relatively small training set, it seems to have actually learned something. Now you can also use this most similar to perform that kind of vector arithmetic that can do the analogies, and also that we saw on the Brown Women Writers corpus. The way you do it is, instead of just typing a word in, you can use the negative and positive keywords. The negative will minus the vector for whatever words you put in this list. And it could be more than one. I've just put king, but you know, you could put other words. And the positive will add the vectors for whatever you put in there. So here's an example. If you wanted to compute this analogy, X is to queen as man is to king. Then you want queen plus man minus king. So we've got minus king, negative equals king, and positive queen plus man. So if you execute that, you'll see that you get the correct answer, woman. And Totoro. For some reason, my neighbor Totoro seems to be related to this analogy somehow. Okay, so my plan now was just to let you play around with these 3 cells for a while and see what you think. See if you can get your head around it. See if you think the model's learnt anything. These down here in this section, I've shown you how you can download pre-trained word vector models. So here's the word2vec model that Mikolov trained, a 300-dimensional model on a huge corpus from Google News. And here's a fast text model that Mikolov later trained at Facebook on a big Wikipedia corpus. So one thing I would say is, if you don't mind, don't try and use these during this class, because they take forever to download. They're quite big because the vocabularies are so huge. So they take a while to download. And when I tried to do this last night, they were taking forever. But in your own time, by all means, you can have a go at using them. It may be better to do this on your own machine. You should be able to do this on an ordinary laptop. Training these models can require some powerful computing resources, but just using the word vectors once they're trained takes very little computing power. So there's no reason you couldn't download this IPython notebook and run it on your own machine and have a go, if you find that it's taking a while to download the models. let's say 5 minutes to play around with these 3 cells here. And then we'll come back together after 5 minutes and have a bit of a discussion of what you think about word vectors. And then to conclude, we'll have a broader discussion about some aspects, what we covered in the course, and some aspects of machine learning that we didn't cover that you may wish to explore. Okay, how did everyone go? Anyone discover anything interesting? Any surprising strengths or surprising weaknesses of the model? Almost. Well, so maybe it doesn't really know that Canberra is the capital of Australia, but this example, it does get Paris at least in the top 10. But you're saying that with more obscure countries, don't get as much play in English language texts. Not obscure countries, but, you know, countries that are obscure in English language texts. Doesn't work so well. Are you sure that the Cotswolds isn't the capital of Ukraine? Yeah, that's the thing. I guess it. We don't really know what's in this corpus, but depending on the corpus, that could be quite interesting. Like if it's a corpus of fiction, oh well, it's perhaps not a very interesting thing to discover that life is spoken about very positively and death negatively. But if it was a corpus of biology articles, which strive to be value neutral, and yet life and death are spoken about in an emotionally charged way, that might tell you something interesting about that corpus of biology articles. So we don't really know what's in this corpus. I think it's just taken from Wikipedia, which again, it could be interesting that in Wikipedia, life and death have these positive and negative associations, though there are a lot of biographical articles, aren't there? And if you tell a biography of someone, death tends to be a negative event in people's lives. So I guess it's inevitable that it'll have that connotation. Doing something totally nonsensical, which was hate minus hatred. So this is how you do hate minus hatred. And yeah, look, I've got the same as you, codex, og, zik, decoder. There's 2 things I would say there. I would suspect that hate and hatred have pretty similar word vectors. So when you minus one from the other, you end up with a word vector that's quite close to the origin point, that's quite close to 0, because they, you know, hate and hatred are probably similar. So it probably takes the vector into sort of a no man's land near the center of the vector space. And you'll notice that these vectors it's supposedly similar to, look at the similarity scores, they're quite low. Like up here, these words being similar to death, like untimely and divorcing and remarriage, the similarity scores are in the 60s and 70s. Whereas down here, these similarity scores are in the 30s and 40s, which you know, is comparatively not that close. These scores are between 0 and 1. I'm pretty sure they've used the cosine similarity here. So that's not that similar. But it is an interesting behavior. It's an interesting thing to note. I mean, you could even do this and see what happens. Hate minus hate. And you see that's equal to 0 because they're the same word vector. And then it's just completely random what words are nearby. And the similarity is 0 because, well, they're 0. That's a vector with no angle. So it can't actually have a, no length, sorry. So it can't actually be compared. It has no direction. Okay, well, I hope you all had a little bit of fun with that and you've got a bit of a sense of what sorts of things these word vector models are able to learn. Now, as I say, here are some pre-made ones you can download and experiment with in your own time. And you'll find that these ones, you know, the results are even better. There's 2 reasons. Number one, the dimensionality is bigger. They're 300 dimensional vectors, so they're more expressive. And the second thing is that they've been trained on absolutely massive data sets. So that kind of segues nicely into a point about machine learning, which is that computers don't really, as I hope you've seen over the course of these 4 sessions, computers don't really learn the same way humans do. You know, when a human learns something, we grasp a situation and we kind of synthesize it in our imagination. And when we change our minds about something, we're quite able to swap from one theory to quite a different theory. You know, we can, there's probably examples of this in your life every day where something comes into your awareness and you think it's one thing and you interpret the situation according to that. And then you realize, actually, no, that's the wrong interpretation. And you swap into a completely different way of understanding the situation. You know, perhaps you hear what you think is laughter, and then suddenly you realize, no, it's someone crying. And your whole attitude to the situation just suddenly alters because you're now interpreting it, you're using a completely different framework. Or, there's a famous example from the Apollo missions, which was when in Apollo 13, they first got the information back from the sensors about the explosion of one of the hydrogen tanks. The first theory people had was that it was instrument funnies, and they were interpreting all of the things they could see on their instrumentation panels as a flaw in the instrumentation, in the sensors. And of course, it then took someone, I can't remember the guy's name actually, who came in and looked at it and he said, no, actually, that's the incorrect interpretation. You need to interpret this as actually something's dreadful has happened to a particular system in the spacecraft. So humans are capable of doing this. Charles Sanders Peirce called it abduction, swapping from one theory to another. Computers can't do that. They learn incredibly, 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 incredibly gradually, and they're only able to learn a tiny bit from any piece of data that's shown to them. So therefore, a model that's trained on 1.6 billion words over a whole day on a massive supercomputer at Google, and which has 300 parameters to tune rather than just 100 parameters to tune, that model's going to learn a lot more than a model that's trained just on a relatively small corpus with just 100 parameters for 7 minutes. But nonetheless, I think you can see that this particular model learns quite well. So I guess to finish off, oh, sorry, I wasn't scrolling. I was scrolling that whole time and trying to show you things on the screen, but the screen sharing was paused. I was just referring down here to the pre-trained models you can download later if you wish. I guess to conclude, there's only some aspects of machine learning we've looked at. We've looked basically at machine learning as applied to text. We've looked basically at 3 main families of algorithm. We looked at, in the first week, we briefly looked at k-means clustering, classical unsupervised clustering algorithm. And then we looked at, we looked at neural networks repeatedly, and also then at an example of a Bayesian network, which was the topic modeling. So we've only looked at those. We've only applied it to text. And there are some aspects of this that I really didn't cover, like some problems that are typically encountered. The biggest problem being so-called overfitting. So all machine learning is when you train the computer to do something on data, you get it to learn from data. The most common problem that occurs is not that the computer can't learn anything good. We've seen that these algorithms work quite well, but that the computer learns something too specific, that it looks at the data and basically it learns to reproduce exactly the data set you've shown it and can't generalize to things it hasn't seen before. And there's a whole host of things people do to try and avoid that. Sometimes it's making modifications to the actual algorithm using so-called regularization techniques. So the ones you often hear of to do with neural networks include dropout or the L2 factorization, I think it's called. I've forgotten what that one's called now. Sometimes another problem is that when you get large and complex models, sometimes the training algorithms don't work anymore. And perverse things can happen and the model can shoot off in the wrong direction and can't gradually converge on a good solution. So people have come up with all sorts of different clever things to make sure that the model, as it's training, does head towards a good solution. And sometimes they can be quite complicated, particularly when you're talking about large neural network models. And there can be these things, residual connections and all sorts of other strange things that people add into the model to stop that from happening. And of course, the biggest problem with machine learning of all is to find a good amount of data, to work out how to represent it so the computer can understand it, and then to formulate a question that the computer can answer, and to work out how to formulate that question mathematically, so that you can tell the computer to answer it. These are some of the things we didn't cover. Yeah, so this is also sometimes called explainable AI. The reason it's become a hot button issue is that nearly all major machine learning systems in the wild that you encounter are run by neural networks. the thing that chooses, Facebook's algorithm for sticking an ad in front of you, the algorithm that turns what you say to Siri into text and then into a command, which then Siri then outputs as some text, which is turned into synthetic speech. All this, it's almost all done by neural networks. Other models do play a role from time to time, and particularly in contexts of decision support. So, for example, when judges use AI to determine bail applications, or a rather taboo subject, but which many people are familiar with, when doctors use a model for nuchal screening to determine whether a fetus is likely to have Down syndrome or some other congenital conditions. Those models tend not to be neural networks, but to be something more like topic modeling, a so-called Bayesian model, for the very reason that they're more interpretable, those models. So a doctor or a judge really wants to be able to interpret what they're seeing rather than just have something happen. So the aim of explainable AI is basically to make AI systems present their results to a human, such that a human can interpret what they're saying and come to a critical judgment. If an AI just says, I'm 0.77 certain that this is iris versicolor and not some other iris, well, okay, you might know from your testing that this model's accurate, so you might trust it that it's probably an iris, but maybe you want to know, why do you think it's an iris, computer? Now, if you're using something like topic modeling, you can actually easily look into the model and you can just see why it thinks something is this topic, because you can see it's got these words and it thinks those words appear in this topic with that probability. Okay, easy. It's quite easy to interpret. But we've seen the problem with neural networks, that they're not interpretable, these sorts of things. And we've seen with word vectors, that come out of neural networks, they're not interpretable either. So people are trying to come up with ways of making neural networks interpretable. And there's various approaches. One way, for example, is to try and visualize the neural network. So you've seen, you can visualize it as a bunch of neurons connected to each other. And what you often see is diagrams where certain neurons are lit up because they've been activated by a certain input. So you can see that if you look at these diagrams, you can say, oh, look, these sorts of inputs light up those neurons. Those sorts of input light up these neurons. And it's kind of analogous to using functional MRI on the brain. By working out which parts of the network activate when, you can get a sense of how the network is analyzing what it's looking at. Another rather kooky example, which you might have seen, that was attempted, this explainable AI, was the deep dream algorithm. So this is now mostly used by artists to generate weird and wacky art. But I'll just show you some examples. I don't know if you've seen any of these before. So you can see, you might recognize that this is Van Gogh's Starry Night, but it's been manipulated. This was actually from an explainable AI experiment. There was a famous image recognition neural network called GoogleNet, which was very good at taking photos and then categorizing them. So it would look at a photo and say, oh, that photo is an example of object number 7 being koala, for example. And it was very good at these challenges, at taking photos and recognizing them. And this same technology is used to, recognize your face on Facebook, for example. And people wanted to know, how is it actually analyzing the image? What does it see in the image? So these guys at Google had this clever idea of running the network backwards. So instead of taking the input image and getting the prediction, they said, okay, let's just run all the calculations backwards and get the network to accentuate those parts of the image that it sees as most interesting. And if you do that multiple times, you end up with a weird sort of image like this. And you can see that there's lots of examples of pareidolia. The computer seems to see faces and eyes everywhere. That's mostly because GoogleNet was trained to recognize animal images. So it tends to see animals in what it analyzes. But you can also see these sorts of geometric patterns. So now it's used to generate art, but this was originally used as a kind of explainable AI experiment to try and work out what neural networks see when they process images. Obviously, in a lot of humanities applications, the black boxness of neural networks can be quite a problem. So lots of humanists prefer to use these non-neural approaches like k-means clustering or topic modeling or similar approaches, which are more interpretable as a result. But you can actually still use models that can't be interpreted because you can test them and validate them by measuring their accuracy. And once you've done that, you may be confident in applying them. There's also ways of interpreting the output without interpreting the guts of it. Like we saw in the Brown Women Writers Project, for example, that once we trust that word vectors do actually represent real relationships between words, it becomes interesting to look at the word vectors and see which words are most similar. And that can maybe tell us something about the nature of discourse in the corpus that we're looking at. And particularly, Hannah, if I remember, you work with collocation networks. Something like word vectors could be used as a discovery tool for you. You know, if you use word vectors to work out which words are most similar to one another in the corpus, that could then be a springboard for you to analyze those particular words using methods that speak to you more directly. So that's I think in the humanities, when you find these neural networks, you most often find them used in a more unsupervised setting. So you've got a whole chaotic bunch of data and you want to extract some order from it. And the way researchers use them is to try and discover patterns in the data. So in that case, it doesn't really matter if the neural network's not interpretable because you're not making firm conclusions based on what the neural network says. Instead, you're using it as an exploratory device to try and work out what things you might want to look at. You know, if these words are similar, you might wonder, oh, why are they similar? I'll go back and look at the texts. Or why are they similar? Are they collocations? You know, if you're using more classical collocation analysis. So I guess we've reached the end. It was a great pleasure to run these. I'm sorry that we missed a week, and I'm sorry there were so many bugs in last week's workshop. Yes, I wish you best of luck with everything going forward.